Well, guys, here we go. This is fun. So I'm pretty sure that I learned this in college. But to be honest with you, I don't remember learning this in college. But, you know, as I was then becoming an AP teacher and sort of pulling together this material for AP, I remember not really appreciating what you're going to learn today, and then actually doing it in front of students for the first time and thinking to myself, this is really pretty cool. So guys, what we're going to do today is we are going to talk about what I talked about when I was driving the homework process. Remember, and I drew your attention to the idea that if we've got 0.5 molar HCl, how do we find the pH of that? Take the negative log of 0.5. And again, why does that work? Because it's a strong acid and it completely dissociates. So the molarity of the strong acids is the molarity of hydrogen or hydronium ion. Good? Okay. Well, guys, today what we're going to do is we're going to talk about the pHs of the weak acids and bases. And in order to do this, guys, we are going to have to bring into this conversation ice boxes. So what we're going to do is we're first of all going to define, again, what are weak acids and bases, but then we're going to start studying them mathematically through the lens of the ice box. And guys, it's sort of interesting because it allows you to apply something that you've already learned. But then what you're going to find out is because we are ice boxing weak acids and bases, something really cool happens mathematically that I really think you're going to like. So guys, here we go. To get started, we first of all need to talk about something called an acid dissociation constant. So guys, grab your AP equation sheets and let's talk. So we are now done with talking about strong acids and bases. Not done, but we're going to put it aside for a couple days. So guys, now what we're going to do is we're going to talk about weak acids. How many acids are weak acids? All of them but 7. So guys, every single substance on this universe that is an acid that isn't one of the big 7 is a weak acid. So what do weak acids do? Well, guys, weak acids, just like strong acids, give away hydrogens, protons. The difference is they don't do it completely. They only partly protonate in water, and instead, of course, what they do is reach equilibrium. No. So protonation is ionization when the ion being given away is a proton. So for acids, they're interchangeable. But we wouldn't say that table salt protonates. It ionizes, but it doesn't protonate. So when the ion is a proton, which is the case for acids, then yes. So guys, do you see the connection? What did I tell you? What kind of math are we going to do today? Ice boxes. Do you now see why? This is really crazy, but this gap in this thing is enough to make me want to look outside. Seriously. If like attention deficit disorder was a thing when I was a kid, I'm fairly sure I would have been diagnosed. I cannot focus. So guys, do you now see the connection? Equilibrium requires ice boxes. We're talking about acids that reach equilibrium, therefore we're going to need to icebox. So guys, here's what I need you to do. We are going to talk first of all generically about these things, and we're going to consider some hypothetical weak acid HA. Here's what you need to do. Write the equation that represents the protonation of this acid. Just write it in your notes right now. I guess I probably should have done this. Who needs an equation sheet? Oh, how about a conversion sheet from general chemistry? Does that do you any good? I'm just kidding. You don't need to keep that. Does anyone need one? Okay. So guys, what'd you come up with? Here's the thing that's cool. I hope that we all didn't get the same answer, right? So some of you, I'm suspecting, wrote down this. Your acid is HA, and this reacts with water, and when it does, what are your products? H3O plus and A minus. So guys, I hope that some of you wrote this down, although it's still wrong. What's wrong? Double-headed arrow. But guys, I think some of you may have written this down. HA in equilibrium with H plus and A minus. Which one's correct? Both of them. Which one are you going to use? It depends. Because remember, guys, we have the freedom to choose the one that we want to use, understanding that these are functionally the same and that acids really form hydronium and not hydrogen ion. But guys, we can use either one. So then the question becomes, which one are they going to use on the AP equation sheet? And the answer is this one. So guys, regardless of the one that you wrote down, here's what I now need you to do. Write the Kc expression for this one. Whether you wrote the top or bottom one doesn't matter. Write the Kc expression for the bottom one. Hey. You need keys plural?
Yes.
I think I only have key singular.
I have a student that's been gone for like 2 weeks. So.
I don't know where those other keys are. Can I get them to you later? I'm going to have to search for them because the only thing I have there is third quarter, so it would just be the most recent test.
Oh, okay.
So,
yeah, no worries, I can get that.
okay, so here, if you're looking for third quarter, why don't you just take the whole folder? There you go. Just take it all and I'll get it back from you. Okay, so guys, Kc expression, right? So when you wrote this out, can I get rid of this and we can still picture what we had? So for our Kc expression then, guys, we've got our products. No, sorry. Here we go. So we've got our products. And then we've got our reactants. Yes? Or no? Yes? Okay, but guys, remember I sort of set you up for failure last time, right? And previously we crossed out part of this because it was a pure liquid or a pure solid. Are all of these, and maybe it would be helpful to write this down. Here's what we're looking at. What phase are these things in? What about HA? Solid, liquid, gas, or aqueous? Aqueous. What about hydrogen ion? Aqueous. What about acid? It's aqueous. So guys, are you real? And you got to tell me no if the answer is no. Are you comfortable with the idea that HA is aqueous? Yes, and that's why I wanted to push, because my fear is you're all just going to go, yeah, sure, but you don't get it. So guys, Mark is exactly right. Weak acids are solids. So let's do this. Imagine if you have a jar of vinegar. Okay, let's make this real world. So guys, you've got a jar of vinegar, and what's going on inside the vinegar is this, and that's the point. Don't confuse soluble with dissociated. Guys, if you've got a jug of vinegar, it's not like there's acetic acid crystals on the bottom and then what's dissolved becomes the vinegar, the acidic solution. Guys, all of this is dissolved in water. The acetic acid, the acetate ion, and the hydrogen, they're all dissolved into water. The difference is that some of it is not protonated. It doesn't mean it's not dissolved. It just means it's not protonated or broken down, but it is still dissolved. Do you get it? Okay, so now guys, compare this with your equation sheet. Looking over at the acid at the equilibrium section, do y'all see it? Where is this dude? Third one down. But guys, you'll notice that we don't call it Kc, right? What do we call it? Ka. Guys, what you just wrote is what is called a Ka expression. This is an acid dissociation constant. Now, Mark, we're going to talk about what you just talked about. So, guys, what does Ka tell you? Well, let's go back and look at the original chemistry. So, guys, this is the equation that we're looking at. So, what does the value of Ka actually tell us? Not quite percent, but you're close. What is it? Don't use the word percent, but what is it telling us? A ratio of protonated to unprotonated stuff. So we're not going to think of it as a percentage, but it is a ratio. So guys, fundamentally what Ka tells us is this: how much the acid falls apart. Because the numerator is the amount that fell apart. So what does it tell us if we have an acid with a big Ka value? What does that tell us? It's a stronger weak acid. So guys, the bigger the Ka value is, the stronger the weak acid. And then conversely, the smaller the Ka value, the weaker the weak acid. Does that make sense? Write it down in your notes if you don't have that and you don't think you can remember it. So guys, fundamentally, Ka tells us how strong a weak acid is. So the bigger the value of Ka, the stronger the weak acid. So guys, then the question becomes this: what does big and small mean? What's our range of values? Well, guys, these are obviously not written in stone, but when we think about strong weak acids, we're talking about weak acids that have Ka values on the order of 10 to the negative third. If you've got a weak acid with a Ka of like negative 0.001 or 10 to the negative third, that's a pretty strong weak acid. So guys, what do weak acids look like? Well, typically 10 to the negative fifth and below. Those are considered the weak acids. So now, Mark, you see how you're not in sort of that limbo land? You can actually talk about strong weak acids and weak acids by looking at their Ka values. So the bigger the Ka value, the stronger the weak acid. But guys, in the world of weak acids, 10 to the negative third is a pretty big Ka value. Say that again. Yeah, and again, it's not like you're going to be asked, is this a strong weak acid or a weak acid? You won't be put in that position, but you can talk about it comparatively. But what you are going to see in a minute is that these ranges of values are going to become important to us mathematically in just a moment. You guys okay with the idea? Okay, so guys, summarizing then, here's what we know. So what we just wrote are what are called acid dissociation constants. We understand that the larger the value of Ka, the stronger the weak acid. And we can use these descriptively and comparatively. But what we're going to do now, and you don't need to write this down, we're going to use this to figure out the pHs of weak acid solutions. So guys, we're going to solve a couple problems. This is really all we're going to do for the rest of the day. So tell me when you're caught up and we'll keep spinning. You guys okay? Okay. So guys, try this. This is interesting. So it goes like this. You as a chemistry student prepare a 0.1 molar solution of formic acid. Guys, formic acid is HCHO2. If its pH is 2.38, what is the Ka of formic acid? And that you should be able to figure out. But then in addition to that, and Mark, this is why I balked at your idea of percentage, we actually are going to talk about percent protonation. What percent of this actually protonates? So guys, first things first, let's let you, well, I should be careful. I'm seeing you guys reach for calculators, which scares me. Guys, what do we do to figure out the Ka value for this? We got to write a balanced equation and then do what? Icebox the thing. So guys, let's do this together, shall we? So here we go. In order to solve this problem, and you understand we're solving for Ka, right? So don't write this down. But eventually what we need is a Ka, which we understand to be products divided by reactants. So guys, what we need to know is the equilibrium concentrations of the products and reactants. That'll let us figure out Ka. So with that said, we know that we need to icebox this to figure out equilibrium concentrations. So to set up the icebox, balanced equation first. So guys, do this with me. HCHO2, and that is in equilibrium with. So this is an acid. What's it going to do? Give away hydrogens. But guys, just listen before you write. Don't write the hydrogens first. You understand that technically it doesn't matter, right? That A plus B and B plus A is the same. But guys, I would encourage you to get in the habit of not writing the hydrogen first. Instead, let's write this first. And now, guys, let's talk about some important things. First of all, that's wrong. Why is it wrong? It's an ion, and what's its charge? Negative. Guys, this has got a negative charge because it lost a hydrogen. Now we need to talk about this. Why did I take away the first hydrogen and not the second hydrogen? And guys, the answer is this. When chemical formulas are written for acids, the acidic hydrogen will always be first or last. So when you see the chemical formulas for acids, there will always be a hydrogen that's either at the beginning or the end. That is the acidic hydrogen. It's never the hydrogen that's buried in the chemical formula. So your acidic hydrogen then is going to be this guy. So guys, with that said, what does that then make this ion? What is that? What name do we give it? Not what name is it, but what role is it playing? Conjugate base. So guys, when we write our balanced equations, we will always write the conjugate base first, and then we will write the hydrogen ion second. So let's review what we just talked about. First of all, how do we know which hydrogen to take away? The acidic hydrogen will be first or last. Then second, we will always write the conjugate base first in the products. It doesn't have to be that way, but it's going to make your life a whole lot easier in chapter 17. And then guys, watch out for the charges on your conjugates because many times they'll be changing because the protons are positive. You guys good there? Okay, so now gang, let's icebox this thing. All right. What do we got, gang? Okay, so we've got a 0.1 molar solution. Where does that go? Left, middle, or right? Left. Top, middle, or bottom? Top. Guys, this is the molarity of the formic acid before it breaks apart. What else do we know? Let's do this. Let's start at the top first. What else do we know up top? These are zeros, right? Do you understand why? No products formed. Initially, there's no products. We're not dumping in any product. We're only dumping in reactant. Yeah? Okay. Guys, what else do we know? And Jake, I think you're on to it. We do know one other thing. Good. Because we know the pH, what is the pH the measure of? The concentration of hydrogen at equilibrium. And I love now that you're grabbing your calculators, because now is the time to grab your calculator, guys, and we will do a side calculation that says that pH is the negative log of hydrogen ion. The pH is 2.38. That's equal to the negative log of X. I hope you guys are faster on the calculator. What's the concentration of hydrogen ion? 0.0042? Is that right? Okay, so guys, look at what that now tells us. Where does the 0.0042 go? Yes, this is the concentration of hydrogen ion at equilibrium. But now, guys, do you see how that one bit of information allows us to fill in the rest of the table? How does it go? If we know this, what do we now know? We now know the change. This went down by went up by 0.0042. So now what do we know? So did hydrogen, right? So did hydrogen, so did the conjugate base. It also went up by 0.0042. So this must also be 0.0042. But now, guys, if that is 0.0042, what happened to the original acid? It went down by 0.0042. And now we can do that math. Why would it be times 2? Yeah, there's no 2 in the balanced equation. There's my calculator. So, guys, what does the subtraction get us to? 0.9958. Okay. So now, guys, we know all the concentrations at equilibrium. So at this point, we do this. And guys, here, watch really quickly. Some people don't do this. So some people will start like this. See what I'm saying? You don't need to do that. You do not have to write down the generic form of this equation. So let me undo as much of that as I possibly can. So guys, you don't need to do that. What you do need to do is write down your actual substances. So it would be CHO2 minus, hydrogen plus, and HCHO2 like so. And now we know all of these. 0.0042 molar squared divided by 0.9958 molar is equal to, yeah. Oh, this is a 0? Yeah. It'd have to be. Is that right? Is that right?
0.0958. No, it's just 0.0958. That's right.
Oh, good heavens. That's right. Okay, so now, guys, let's do the math. 0.0042, square that, then divide that by 0.0958, and we get 1.8 times 10 to the negative 1, 2, 3, 4 times 10 to the negative 4th.
That Ka doesn't have.
There are no units on K. What do you think, guys? Right, and so we're not done. There's many things that we need to think about and then also still do. So, guys, first of all, are you okay with the icebox? Okay with the way the pieces fit together? Okay with the calculation that led us to Ka? You're okay? Now let's have this conversation. Is that a strong or a weak acid? Kind of in the middle, right? We said -3 and up is pretty strong. -5 and below. So it's sort of on the borderline. But now, guys, we're going to do this. We're now going to figure out the percentage of this acid that is protonated. So So guys, what we know is that this acid has a Ka of 1.8 times 10 to the negative fourth. So how much then of this acid is actually broken apart? Well guys, in order to figure that out, here's what we're going to do, and this is new, you want to write this down. So what we're going to do is we are going to calculate what is called percent ionization. Percent ionization is equal to the concentration of hydrogen ion divided by, you know what, let's use our previous structures, divided by the no, you know what, I don't even want to do that. Let me get rid of this. Divided by the concentration of the acid initially. So think about what we're saying. The hydrogen ion concentration at equilibrium tells us how much of it broke apart. The initial acid concentration tells us how much of it was there to break apart. So guys, going back to our initial setup, we had 0.0042, this number, as our concentration of hydrogen ion, and this number is our initial concentration. So this would then be 0.0042 molar divided by, was it 0.1? Divided by 0.1 molar, and then to convert that into a percentage, we'll multiply it by 100, but it's 0.0042 divided by 0.1 times 100. Guys, 4.2%. That's protonated. That's not, and that's the point. Guys, we said that formic acid, given its Ka of 1.8 times 10 to the negative fourth, that's a relatively strong weak acid. And as a relatively strong weak acid, guys, only 4% of it's broken apart. So what does that mean? Well, if we had a bucket of formic acid, this is going to contain, and I never remember the formula, this is going to contain HCHO2 and CHO2 minus and H plus. So guys, what do the numbers look like? Well, in round numbers, we got 4% this, 4% this, and 96% that. So in this weak acid solution, 96% of that formic acid is still stuck together with its hydrogen, and it's not functioning as an acid. It is in its molecular form, dissolved in water. Yeah. I'm sorry? No, but what we're saying is that, okay, so 4% of it's broken apart. So at any given moment, 4% is broken apart, 96% is still stuck together. Go ahead.
So, and just kind of like round it, if we say this is, you know, the negative 4, we say it's the negative 3, it's only like 40% of the strongest weak acids are propane. Sorry, so only 40%, only about 40%, like if it's strong, the strongest of the weak acids, only about 40% of it was propane.
Oh, I see what you're saying if we up this by a power of 10, and if we said Ka was 10 to the negative third, then what would be the percent protonation? We're actually going to calculate it in just a second. But no, it wouldn't, because it wouldn't be 40%. You wouldn't multiply this by 10 because the pH would change, and it would, so it's not a direct conversion, but your thinking's not incorrect. It's just not quite proportional. But yeah. You guys okay with everything we just talked about? You're okay with percent ionization? You're appreciating the idea that this number is pretty darn small, and you're good with this math. Is that true? You're good? All right, because guys, this is about to get interesting. So let me go here and here. That's fine. I'll put the fresh page here. And guys, we're going to solve one more of these. That's all we need. So guys, now we're going the other direction. Previously, we were given the pH and we calculated Ka. Now we're given Ka and we are going to calculate the pH. So guys, do this with me. To start, we need a balanced equation. CH3, COOH. I'm going to write the conjugate base first. You'll thank me in unit chapter 17, and then the protons. Now guys, we set up our icebox. So now gang, let's talk. What are we given? What can we write in? Top left. We know that this is 0.30 molar. What else can we write in? The zeros. What else can we write in? Nothing. Guys, that's it. So before we start straining our brains to figure out what we're going to do next, guys, let's have this conversation. What are we solving for? So we're solving for pH, right? So where in the icebox is pH? Lower right-hand corner. So guys, and you don't need to write this down, but this is our goal. Because if we can figure out the molarity of hydrogen ion at equilibrium, we can then take the negative log of that, and that gives us pH. Does that make sense? Okay, so now guys, with that idea in place, let's now talk about how we're going to represent equilibrium. What did you learn in the last unit? What do we have to do? Use X's. So guys, here's what we're going to assume. When this breaks apart, the acetic acid is going to break apart by a factor of X. So if that breaks down by X, how much, what will this change by? This will go up by X, and this will go up by X. So then, guys, at equilibrium, this will be 0.30 minus X, this will be X, and this will be X. Does that make sense? Okay. Now, guys, check this out. Do this exactly the way I'm doing this, because this is the way you're going to do it on the test, and you're going to like this. Bradley, it sounds like you're leaving. So, guys, here's the way, and this will be screencasted. So, guys, here's the way this goes. Write this down with me. Ka. We're now ready to figure out the concentration at equilibrium. So we're going to go Ka is equal to CH3 COOH. Oh, no, it's not. Don't write down that with me. CH3 COO minus, hydrogen plus, and CH3 COOH. Now, guys, this is where this gets good. Actually, you know what? Maybe not equal signs there. It's a little misleading. So now, what's our Ka value? 1.8 times 10 to the negative fifth. We've got to be given that. Is equal to, what is our concentration of acetate and hydrogen? X. So we're going to call that X squared. Now in our denominator, what is our concentration of unprotonated acetic acid? Or I'm sorry, protonated acetic acid? Or it is unprotonated. CH3COOH minus, what am I doing? Guys, I'm sorry. I'm trying to figure out how to formulate this as I write it down for you. And I'm writing as I'm thinking. So guys, this is 0.30 minus X. Now guys, stop. What do we have to do to solve this for X? What's it going to look like? We're going to cross multiply, gather terms. What will the expression look like? We're going to end up with a x squared and some factor x and then some other numeral that will be equal to 0. And then we throw that in the quadratic formula and solve it, right? Does that make sense? You guys good on that? Because guys, guess what? We don't have to do that. Guys, check this out. This is magic. You ready? Why do we have to solve this using the quadratic formula? And the answer is this. The answer is that when we cross multiply this, we then end up with a polynomial that can only be solved using the quadratic formula. But now, guys, follow this logic, because this is really cool. What does this number right there represent? What does that number represent? What does that number represent? What does that number represent? It's not a change. This whole thing is the change. What does that number represent? The amount of acetic acid that does what? Falls apart, right? Does that make sense? Now, guys, ask yourself this question. How much of that acetic acid is going to fall apart? A lot or a little? What makes you believe that you're right? What is it that makes you believe it's going to be just a little? The Ka value. Now, guys, put this in context. And that's why we did formic acid first. What was the Ka value of formic acid? 1.8 times 10 to the negative fourth. So it's stronger than acetic acid. So guys, formic acid is 10 times stronger than acetic acid. And how much of the formic acid fell apart? 4%. So how much of acetic acid is going to fall apart if its Ka value is 10 times smaller? About 10 times less. So like 0.4%. Does that make sense? So guys, look at what we just said. We said that this value for X represents the amount of acetic acid that's going to fall apart. But now we know, based upon the Ka value, that X is going to be itty-bitty. And guys, it turns out that it is so itty-bitty that we can get rid of it. So guys, here's what, and guys, you got to understand the logic or you don't get to do this on the test. Why is it we can get rid of that X? The reason is because the amount that this acid falls apart is so small compared to its original concentration that the change will be so insignificant that we don't need to worry about it. Hold on. Now, what is that logic based upon? The value of Ka. Ka is so small that it tells us that this is going to be small compared to the original concentration, and consequently, we can ignore it. Now, guys, I'm not even going to think about questions. Let's keep going. So how do we represent this? Guys, watch what I'm going to do. Here's how you represent this. You say approximately equal to x squared divided by 0.30. That's the way you represent this on the AP test. So what we've said is we're getting rid of the minus x and saying that is approximately equal to simply the x squared divided by 0.30. Now, I'm not doing questions. Now, guys, let's finish with the math. So how do we now solve this? Well, all we have to do is cross multiply. So we're going to go 1.8 times 10 to the negative fifth and then multiply that by 0.3. Then what do we do to solve that for x? Take the square root, and the answer to this, and you don't have to show any of that math, but the answer to this is 0.00232 molar. Well, yes. So actually, why don't I just do that too? So now, guys, we're ready to finish the problem. Do you see how this fits together? What is this number? Well, it's this number. It is the hydrogen ion concentration. So now all we have to do is go pH is equal to the negative log of hydrogen ion is equal to the negative log of 0.0023 is equal to, I don't trust you guys anymore. That's true. So 2.64. So guys, do you understand the process and that? And I'm still ignoring questions. I know your questions, and I want to get there because they're great questions. But do you understand the process in the math? Okay, now guys, do this with me. Percent ionization. Percent ionization is equal to concentration of hydrogen divided by the concentration of the acid. Oh boy. The concentration of the acid initially is equal to 0.0023 divided by 0.3. So 0.0023 divided by 0.3 times 100, guys, 0.77%. This acid is so weak that only, well, let's say it the other way, 99.23% of it is not protonated at 0.3 molar. Do you get the idea? Okay, so now let's talk about your questions. Go ahead, Matt. Right. So when does this work? So guys, you ready? If you don't understand Matt's question and Mark's question and probably Jake's question and Becca's question, because it's the question. So guys, here's the thing that's painful. This could become cyclic. So let's talk about the logic. Why were we able to get rid of the X? Because it's very small. How small is it? 0.77%. So we now know that, yeah, it was appropriate to get rid of that X because it's so small, it's actually 0.77%. But the problem is that in order to verify that in fact it is that small, what we really should do is solve the equation using the quadratic formula, find out what the percent ionization is, and then if it was small enough, we could go back and say, well, we really didn't need to do that. We could have just got rid of it. But that's stupid. So guys, here's the rule. 5%. That's the rule. 5%. If an acid protonates less than 5%, you can drop the X. But that's still weird, right? Because you don't know the percent protonation until you get done with all the math. So how does this line up relative to Ka values? And guys, this is where we come back to what I shared with you a second ago. So if the Ka is smaller than 10 to the negative fifth, your money. If the Ka value is on the order of 10 to the negative fifth and smaller, you're gold. If the Ka value is greater than 10 to the negative third, you cannot drop the X. Because a Ka value we should say at or equal to, a Ka value at or equal to 10 to the negative third is big enough that minus X is significant. So then, guys, the question becomes, what about 10 to the negative fourth? And the answer is, be careful. But I've never seen it on the AP test. On the AP test, I've never seen them throw a weak acid at you where the Ka value was 10 to the negative fourth. It was either 10 to the negative fifth and smaller and you could disregard it, or it's 10 to the negative third and bigger and you couldn't. I've never seen the gray area. So now let's wrap up other questions. Go ahead.
So the other day when we were talking about conjugate bases, the like very strong acid, strong acids.
Right.
Like what kind of protonation?
That's what we're doing next. Yeah, we're going to talk about the conjugate base, but the answer is they're the same. But instead of talking about Ka, we're going to talk about Kb.
So something about like
Just trust me, we're going to answer your questions in just a minute.
I'm talking about the strength.
I understand. I promise you. Go ahead.
So when we kill the X,
Yeah.
because it's so insignificant,
Mhm.
why do we need the X squared? Because the tiny number of squares.
Right, yeah. So if we get rid of the X, why isn't this insignificant? And the answer is because it is. It's equally small, but it's also the pH. So now we understand that those pHs are relatively small. So down here, this minus X is bitty compared to the 0.3 molar that it started at. But now when we think about this X as representing the hydrogen ion concentration, it's no longer insignificant. As a matter of fact, it's enough hydrogen to give us a pH of 2.6. Does that make sense? That's a great question. So guys, let's now look at the other potential side of this, which is where Jake's brain is going. We already talked about these rules. Now we got to talk about weak bases. Write this down with me. And Jake, understand, I know this isn't directly your question. We're going to get there about that relational thing in just a minute. Okay, so guys, the idea then is this. We understand that weak bases, like weak acids, are substances that only partly protonate water. So the difference is that we've got to have water. So guys, we can only understand weak bases in the context of water. So do this with me. Let's write the chemical equation for a weak base acting in water. So do this with me. We've got base, I want to switch colors. We've got base and we've got water. Write in the products. What are we going to get? What's the base going to do to the water? It's going to take in a hydrogen. Let me write this the same way they do. So when it takes in a hydrogen, we're going to end up with Hb plus. And then what happens to the water? It becomes OH. So now, guys, let's write the Kc expression for this. What's the Kc expression going to be? Hb plus OH minus, what goes on the bottom? B. What about the water? No. The water is a pure liquid. Therefore, it does not go in the denominator. Guys, find it on the AP equation sheet. Do you see it? You guys good? Okay. So now, guys, we're going to do this. Let's figure this out then. So, guys, let's figure out the pH of a 0.15 molar NH3 solution. 0.15 molar NH3. We're not going to take it to completion, but let's at least get started. So the question is 0.15 molar NH3. What's the pH? So guys, let's set up the icebox. So we've got NH3. We've got water. Do we need the water? Yes. Without the water, this isn't a base. In equilibrium with NH4 plus and OH. So now, guys, we icebox this. And let's switch to red. What do we know? Yep, 0.15 is NH3. 0, 0. But guys, what about the water? Is that a 0? It's not. Guys, it's gone. Scribble it out. Don't confuse 0 molarity with can't have a molarity. So it gets scribbled out. It's got to be in the equation or it won't balance, but it's not a participant in the equilibrium. So then, guys, just like before, this goes down by X. These go up by X. So this is 0.15 minus X. This is X. This is X. Let's look. So then, guys, when we write the Kb, we've got NH4, hydroxide, and NH3. But now, guys, to solve this, what do we need to know? We need the Kb value. It wasn't given in the problem, but it would have to be given to you. We can look it up in Appendix C, or it's actually there's a table of them in the book. And the value is, I think it's, here it is, ammonia. Oh yeah, right. It's actually, guys, the same as the Ka value for acetic acid. Don't read anything into that. I just got that off of page 676. So then we get x squared all divided by 0.15 minus x. Now, can we do the squiggly approximately equal to thing and get rid of the minus x? We can. How do we know? Because the Kb value is 10 to the negative fifth. That is small enough that the negative x is insignificant. So we end up with x squared all over 0.15. So we can go 1.8 times 10 to the negative fifth times 0.15 square root, and I get 0.0016. Now guys, how do we find the pH? Take the negative log of that? No. Because what does that represent? The OH concentration. So we can go POH is the negative log of OH, and then we can find the POH and then subtract it from 14 because pH plus POH is 14. You get the idea? So guys, I know this is wildly unsatisfying, but we're not going to finish this problem. I know. Is it going to kill you?
Yeah.
All right, let's finish it. So 0.0016. So that means this has got a POH of 2.78. Then pH plus POH is equal to 14. So pH is equal to 14 minus 2.78, which is 11.23. You good? All right, now we're satisfied. So guys, let's wrap up the day. One last thing we need to talk about. So guys, the last thing we need to talk about is what Jake is starting to see. We now understand that we can measure the strengths of acids. How? Ka values. We can also measure the strength of weak bases. How? Kb values. But guys, what then about this? Let's say, for example, we have acetic acid and we have acetate ion and hydrogen. So guys, this is an acid, right? What's this? A conjugate base. And what did we say about the relationship? The stronger the acid, what will be true of the conjugate base? The weaker it will be. So think about it this way. How do we represent the strength of a weak acid? Ka. How do we represent the strength of a weak base? Kb. So as Ka goes up, meaning this is stronger, Kb for the conjugate base will go down, meaning it's weaker. And guys, that is not just a generic relationship that says as the Ka of an acid goes up, the Kb of the weak base goes down. It's actually a mathematical relationship. And guys, the mathematical relationship, which is also in your equation chart, is this. Ka times Kb is equal to Kw. So for example, if we look at our acetic acid system, we know that the Ka of acetic acid is 1.8 times 10 to the negative fifth. That's a pretty strong, it's not terribly strong, but it's kind of strong. Guys, the Kb for acetate ion is actually 5.6 times 10 to the negative 10th. So for stronger weak acids, we'll have weaker conjugate bases, but now we can quantify that rather than talking about it generically. And that was kind of where you were headed, right?
So, and then more specifically, like if I say hydrochloric acid,
Mm-hmm.
I mean, I know it's not the exact same, but like if it were to treat that as if it was a weak.
As if it were weak, right?
I mean, then the Ka would really, I mean, it wouldn't have.
So the Ka is infinite and the Kb of the conjugate base, chloride, is 0. We call it strong and negligible, but it's really infinite and 0.
So, we say negligible, is it actually 0, or we have like?
There's always a little.
Yeah.
I mean, the law of averages would say there's always a little.
So it's gonna be like 10 to the negative 5, 10 to the Google.
It's very, very small. You guys good? So guys, here's your homework. Coming at you. Let me stop recording.